This lecture is going to be over Chapter 6. We're going to be looking at all four sections of this particular chapter, and there's going to be a lot here at the beginning. So let's just go on in with section 6.1. And actually, before we even do that, there is a summary here at the back that gives you a flow chart as to what happens when radiation starts interacting within a substance. And if you look at it from interacting with a patient, you have two different ways in which this can happen. You've got non-ionizing radiation, in other words, in which no ionization takes place, or where ionization takes place. If ionization were to take place, you would have two different types. You have direct ionizing and indirect ionizing. If it's direct, then charged particles will cause ionization and excitation, as well as free radical formation, which will lead to biological damage. If it is indirect, then you've got a two-step process. It set charged particles in motion, and you can have three different types of interactions here, which we will go over, which again lead to this step and then eventually to biological damage. So these are the types of things that can go on once radiation is present inside someone. So this flow chart, along with the information that comes after it, these are going to be the important things that you will need to remember. This rule of thumb is going to be something that you're going to need to remember, particularly for electrons. That is a very good test question. That is also a very good registry question. So there are lots of things here in this particular summary. Summary is very good, but let's go through the sections here and discuss a little bit about what the summary here should be. All right. Again, radiation can be characterized as either indirectly ionizing or directly. Fast charged particles are directly ionizing radiation. They can deliver energy to matter directly by many small interactions causing atomic excitation and ionization, which will lead to biological damage. And examples of fast charged particles are electrons as well as protons. Neutral particles, photons, and neutrons are indirectly ionizing. They transfer energy to charged particles, then the charged particles deliver energy into the matter. Therefore, the energy transfer is going to be indirect, and it's a two-step process. So in other words, this is, if you are looking at electrons and protons, this again, you are looking at how they deliver energy into matter, causing atomic excitation and ionization. Whereas the neutral particles here are indirect. They are going to transfer energy to the charged particle, and then the particle delivers the energy into the matter. When two objects collide with one another, they come into when two objects collide with one another, they come into contact. It is not clear what contact means for elementary particles. The rules are a little different there. Anytime a free bombarding particle interacts with another particle, physicists refer to this as a quote-unquote collision. So it's not necessarily like a billiard ball collision or a hit and run, that kind of thing. If you get close enough here, that's going to count as contact. So you have two types of collisions, just as if you were studying Newtonian mechanics. You've got elastic and inelastic. If it's elastic, then the total energy of the particles before the collision is going to be the same as the total kinetic energy after the collision. Often the kinetic energy of the bombarding particle doesn't change. An inelastic collision is one in which the total energy of the incident particles changes. Total energy must be conserved, and therefore any kinetic energy lost must appear elsewhere in some other form. And that lost kinetic energy appears as some other type of energy, like excitation energy, ionization energy, Bremsstrahlung, and Bremsstrahlung production, where a bombarding electron interacts with an atomic nucleus in an X-ray target, loses some of its kinetic energy, which then appears in the form of an X-ray photon. So the difference here between absorption and scattering: in absorption, the photon is destroyed and ceases to exist. Therefore, it is absorbed into the material. Whereas in scattering, the direction of the travel of the photon is changed, and hence the photon may effectively be removed from the useful beam. So when a photon interacts with matter, you've got two microscopic entities in which it can interact. You've got electrons or you've got atomic nuclei. In other words, you're going to be hitting some part of the atom as the photon goes through. Highly energetic photons can interact directly with individual nucleons. However, this is unimportant for what we're doing. For some interactions, there's an energy threshold below which the interaction will not occur. So for a given photon energy, several different types of interactions might be possible. Different interactions occur with varying probability, and it depends on the energy and the composition of the matter. We'll get to that. The dominant interaction mechanism is going to be determined by the energy of the photon and the atomic number of the material. So when photons interact with electrons, you're going to have three major types of interactions. You're going to have coherent or elastic scattering, photoelectric effect, and Compton scattering. When they interact with nuclei, there's going to be two major processes. It's either pair production or photonuclear reactions. So let's start off here with the coherent scattering. The photon is deflected or scattered without any change in its energy. And that's an example of an elastic collision. It's only important at very low energies and for materials with a high Z value. If it's the photoelectric effect, the photon is absorbed and the energy is transferred to an atomic electron, which is then ejected from the atom. This is important in diagnostic X-ray energy and dominates at low energies for the high atomic numbers. Compton scattering is going to be the process in which the photon interacts with an atomic electron, giving up some of its energy and changing direction in the process. Compton effect is the predominant photon interaction in soft tissue in therapy range. So that's something we're definitely wanting to study. When a high energy photon passes close to an atomic nucleus, the photon energy can be converted into matter. And this energy of the photon appears in the form of an electron-positron pair. And that's why we call it pair production. Now you can see here, you've got photon energies in MV, and you've got the atomic number of whatever it's going through. As if you look at the energy in this range, the higher the atomic number, you're going to see here that the photoelectric effect is really what's going to be going on. Now, you still, if the atomic number is low enough, you can still have the Compton effect being dominantly what's going on. At the higher energies, not that I've seen anybody use a 50 or 100, but at the higher energies and the higher atomic numbers, you're going to see pair production dominate. But still, if it's a low Z material, you could still have a domination of the Compton effect. You can see here within this range up to about right here, you're going to see the Compton effect be the primary thing that you're going to see happen. Now, some of you, I'm sure, will note that, hey, you know, a lot of clinics that we have here have photons somewhere, you know, around 5, 10, maybe even 15. And that is true. So why don't we see more pair production? Well, The reason we don't is because the atomic number of the absorber in many of these cases is still going to be within the Compton effect, because for the human body, which acts a lot like water, you're looking at an atomic number roughly around 7. So you're still going to be seeing a lot of the Compton effect still go on. So, as in the figure above, the linear attenuation coefficient for the photoelectric effect acting alone is going to be tau. It's the linear attenuation coefficient. Remember that stuff in chapter 5 that we went over that I'm sure a lot of you hated? That's the kind of stuff it's talking about here. In other words, how is the photon beam, how are we stopping that primary beam as it goes through the material? And how quickly is that happening? And that's going to be our linear attenuation coefficient. So for photoelectric effect, it's called tau. The linear attenuation coefficient for the Compton scattering is going to be denoted by sigma. For pair production, it's going to be denoted by kappa. Along the curve labeled sigma is equal to tau, which is this right here, this line. The Compton and the photoelectric effect, or photoelectric linear attenuation coefficients, are going to be the same. In the area to the upper left, low energy and high Z, the photoelectric effect is going to dominate. If sigma is going to be equal to kappa along that curve right here, then you're going to see the linear attenuation coefficient for Compton scattering be the same as pair production. So now on to a little bit of description here regarding coherent scattering. This is where the photon interacts with an electron and just simply changes its direction. And there's no change in the energy of the photon, just a change in the direction. That's an example of elastic scattering, where the coherent scattering is the only important for photons of very low energy and for high Z materials. It's not something we're looking at here for radiation therapy. But coherent scattering is the reason that the sky is blue. So when you look at the sky away from the direction of the sun, the photons that reach your eye are photons that have been scattered by oxygen and nitrogen in the atmosphere. And so the probability of coherent scattering is inversely proportional to the fourth power of the wavelength of the radiation. So therefore, coherent scattering is much more efficient for blue light than for any other color, and that's why you see it. This also implies that coherent scattering is efficient for ultraviolet radiation, so even if you're out of the direct sunlight, you can be exposed to a considerable amount of UV if your skin is exposed to a large amount of the sky. Now, that's coherent scattering, not something we're really all that interested in. However, we're starting to look at the photoelectric effect, and this will be something that we're interested in looking at. So in the photoelectric effect, the photon interacts with an atomic electron and is totally absorbed by the atom and therefore ceases to exist. Atomic electron gains an amount of energy equal to the energy of the bombarding photon and is ejected from the atom. So some of the absorbed energy is used to overcome the binding energy of the nucleus, kind of like paying to get out of jail, that kind of thing. And any remaining energy appears as kinetic energy of the electron. And that electron is called a photoelectron. And if E sub gamma represents the energy of the bombarding photon, and E sub B is the atomic binding energy of the ejected electron, then basically the kinetic energy of the photoelectron is going to be whatever was in the photon minus whatever it took to get out of the atom. So for lead, the K-shell binding energy is 88 keV. So if you've got a 90 keV photon coming along, it can be absorbed, and that K-shell electron goes out, and it'll have a little bit of change here to go with it. 90 minus 88. So the photoelectric effect can't eject an electron from an atom, unless, of course, you can meet that energy threshold. Otherwise, it just won't work. Once it's ejected, then the characteristic X-ray emission of an Auger electron will follow, and the photoelectric process is essentially likely to occur when the photon energy just exceeds the electron binding energy. The electron binding energy depends on the atomic number of the atom and on the specific shell. There's a sharp rise in the mass attenuation coefficient with the photon energy just exceeding the binding energy of the cell. On a graph of the attenuation coefficient as a function of energy, that sharp rise is going to be called the absorption edge. Now, let's take a look at this. So you can see, and we'll talk about this in just here in a minute, but this is the sharp edge. It's kind of what they're talking about right here. So the mass attenuation coefficient for the photoelectric effect, no other absorption or scattering process operative, is going to be denoted as tau divided by rho. Now, this is photoelectric effect. Now, the reason we're going to focus on this is because there's going to be a lot more that's going to be put into this when we look at adding all of these particular categories together. The general dependence of this quantity on atomic number and energy is approximately this. So in other words, the mass attenuation coefficient is going to be Z divided by E gamma, all of that raised to the third power. So it's going to be directly proportional to Z cubed, inversely proportional to the energy cubed. So it rises very rapidly with increasing Z and falls very rapidly with increasing E sub gamma. And the strong dependence on Z has important implications in diagnostic radiology. The ability to discern structures in a radiograph depends on the relative opacity or contrast of the adjacent tissues. Most soft tissue consists predominantly of water, but bone has a lot of calcium and therefore has a relatively higher effective Z value than water. And that's why bone is very opaque to X-rays in the diagnostic energy range and will show very clearly in a radiographic image. Soft tissues will not. This equation here also forms the basis for use of radiographic contrast agents such as barium and iodine. And both of those have high Z values and therefore very radiopaque. So now that we have kind of gone through that, we can look at figure 6.2. So the mass attenuation coefficient for lead and for water, you can see those here. And this is as a function of energy. So the mass attenuation coefficient for lead is going to be much larger than that for water because this has a higher Z. And you can see here, lead has a Z of 82, water has an effective Z of 7.4. The rapid drop in tau divided by rho with increasing energy is described here. As the energy of the bombarding photons increase above the threshold for the L or K ionization, you get a very sudden rise here in the mass attenuation coefficient. And this is why they call them the absorption edges, because it's not, the curve is not smooth at that point or an edge. Now, Compton scattering. This is going to be the most important part or the most influential on radiation therapy, I should put it that way. It dominates in soft tissue in the ranges of 25 keV, approximately 60 to 100 kVp to 10 MeV. And you can go back and you can look at the chart of 6.1. That figure and kind of see what we're talking about. The effect in the Compton effect, the bombarding photon interacts with an atomic electron. The electron absorbs some. Now remember, in the photoelectric effect, it absorbed all of it. Well, not quite all of it, but there had to be enough there in order for there to be to have a little bit to overcome whatever the binding energy is. It may have a little bit, so I need to correct that. So you can see here that the energy absorbs some of the photon energy and is ejected from the atom, often with substantial final kinetic energy. In many of the cases we saw there with the photoelectric effect, there wasn't very much energy left over. Here, there's going to be considerably more. The photon, therefore, loses some of its energy and is also deflected in its path. The reason for that is to conserve momentum. The electron will have a significant amount of kinetic energy, and in this electron that will deposit dose, and it is this electron that will deposit dose as it moves through the material. So you can see here, you've got this photon comes through here, interacts with this electron. As it does so, it imparts some of its energy to this. When that happens, you get a different photon coming out here, and it's going to be pointed in this direction, and it's going to have less energy than what this had. In order for it to deviate off of a particular linear path here in this direction, momentum has to be conserved. And the only way you do that is if the electron goes off in such a way that momentum is conserved. So it'll be at a different angle here. And that's the reason why. So you can see here, it absorbs some of the photon's energy, is ejected from the atom. Direction changes by an angle theta with respect to its original direction of motion, and now has lower energy. So you can derive an expression relating the final energy of the photon to its initial energy in the angle. This equation is derived by setting the total energy and the total momentum before the interaction equal to the total energy and momentum after the collision. There's a lot of math that goes along with that. We're not really that concerned with it. But the final photon energy is basically the initial divided by all of this junk. Now, alpha here happens to be E sub gamma divided by the rest mass times c squared. And this for an electron happens to be this particular value. It's based on the assumption the electron is initially unbound to an atom, and it's a good approximation when the photon energy is much higher than the electron binding energy. So there are important limiting cases for this when the energy of the incident photon is much larger than the rest energy of the electron. And that occurs when alpha is much, much greater than 1. So if alpha is much, much greater than 1 and theta is equal to 90 degrees, then the cosine of 90 degrees is going to be equal to 0. So when that is the case, then the cosine of 0 from this formula here, that part disappears. So when that disappears, you end up with this. That if you add 1 to this, they're saying, adding 1 to that's really not going to change things that much. So roughly equal to the initial energy divided by alpha. We know what alpha is, so we put it in there. It becomes this, and this becomes the new energy of the new photon. So the maximum photon energy for a photon scattered at 90 degrees is going to be this. If we have something that is emitted at 180, then we have the energy of the afterward photon is going to be this. So the maximum energy of a backscattered photon is going to be this. These limiting case relationships are going to be important later on dealing with shielding. So the energy given to the electron from the scattered photon is going to be the difference required by energy conservation. A photon cannot give up all of its energy in a Compton interaction, and therefore the energy of the recoil electron will always be less than the initial photon energy, because you can't have more than what that initially had, that photon had as it was coming in. So the maximum possible energy is delivered to the recoiling electron when the photon is backscattered. So in this case, that difference there is this, and the electron will move in the direction of the bombarding photon. So let's see, we'll get to an example here in a minute, and it illustrates an example, an application of this and a calculation of the recoil energy of the electron. Here you can see the energy of a Compton scattered photon as a function of the energy of the incident photon for scattering angles of 45, 90, and 180. So let's say you have a gamma ray photon from a cobalt-60 source, and that's scattered through an angle of 10 degrees. What is the energy of the scattered photon? Well, alpha is going to be equal to this expression. We know what the incident energy is. We divide by this, and we come up with 2.45, and therefore all of this, if we put in all of the values that we know, turns out to be 1.21 MeV. So it kept most of its energy here. So what is the kinetic energy of the recoil? The kinetic energy of the recoil electron is going to be the difference between the two, because that's where the energy went. And so it's 1.25 minus 1.21, or 0.04 MeV. It is not possible to predict with certainty the scattering angle for an incident photon of a given energy. You just don't know. There's no way to know. But it is possible to predict the probability of scattering through any angle. At low energies, scattering is almost equally probable in all directions, which is what some of these shapes are trying to denote to you. In other words, it could be emitted pretty much anywhere around that particular electron. As the energy increases, the scatter becomes more and more forward. In other words, it's far more probable. As you can see here, you've got an incident photon of 0.01 MeV. It can pretty much go anywhere. 0.1 MeV starts to force it a little bit in this direction. 1 MeV does a lot of forcing in this direction. 10 MeV means that there's a lot of probability that it's going to be narrowly deflected. The mass attenuation coefficient for Compton scattering will be sigma over rho. As Compton scattering involves photon scattering by atomic electrons, this depends on the number of electrons per gram. And it turns out that sigma divided by rho is directly proportional to the electron density. The number n sub a is the number that can be calculated from the electron density for chemical elements. The number of atoms per gram, n sub a divided by a sub w, where a sub w is the atomic weight of the element in grams per mole. So each atom has z electrons, so it's going to be proportional to this value. So for all elements except hydrogen, this is 2 times z. So n sub e is going to be equal to Na divided by 2, which is independent of z. In other words, it doesn't really matter what your z value is going to end up being in this particular case. So for hydrogen, A sub W is equal to Z, and therefore the number of electrons, or the electron density, I'm sorry, is equal to N sub A, which is Avogadro's number. So the Compton mass attenuation coefficient is roughly the same for all materials, except for those rich in hydrogen. That's the only case in which it doesn't work. The value of rho divided by sigma varies relatively little with photon energy for energies less than about 1 MeV. If you go above that, then you do have a little bit of energy dependence, which leads us to pair production. When E sub gamma is greater than twice the electron's rest mass energy, 1.022 MeV, it becomes possible for the bombarding photon to disappear and be replaced by an electron-positron pair. The charge is conserved in this process. If a single particle, either an electron or positron, were produced, charge would not be conserved. So pair production can occur when a photon with an energy above the threshold passes close to an atomic nucleus. Now, this is sort of what we've got going on. We've got this going on. We've got the photon. Now, it doesn't have to come in contact with it, just has to come close. When that happens, this photon ends up becoming two particles, an electron and a positron. And of course, they're moving away at different angles here in order to be able to conserve momentum. This is actually energy becoming mass, which is kind of weird. So we've got ionization tracks in this picture that result from the pair production process. So you've got a photon that comes in at the bottom and interacts with the nucleus at point A, which is what you're seeing here. And it produces an electron-positron pair. The track of the photon is not visible because it is a neutral particle. It does not produce an ionization track. If you apply a magnetic field, it causes the electron and positron tracks to curve in opposite directions. And so the electron collides with a second electron at point B, producing a delta ray and losing about half of its energy in the process. The other tracks are thought to be produced by Compton recoil scattering. So the positron created in pair production will eventually annihilate with another electron in the matter to produce two 0.511 MeV photons. These photons are sometimes called annihilation radiation. So two photons are produced traveling in opposite directions because otherwise momentum would not be conserved. So the mass attenuation coefficient for pair production with no other processes is kappa divided by rho. Kappa divided by rho is proportional to the atomic number, and it increases with increasing energy above the threshold. Now, those are all of the interactions that the photon that you can see here with a the coherent scattering, the photoelectric effect, and the Compton scattering. This is what you're seeing when they come in contact with the electrons. Now, the pair production, again, remember, is one of those cases in which the photon is coming in and interacting not with another electron, but instead a nucleus. It's just getting close, and this is what happens. Kind of weird that way, but that's where we are. Photonuclear reactions are important because they produce unwanted neutrons, and it's sometimes known as a gamma neutron reaction because the photon comes in and a neutron goes out. In other words, this is before and this is after. The absorption mechanism does not contribute significantly to the attenuation in patients. It does occur with some efficiency in high Z jaws and collimator of a linear accelerator treatment machine. It can produce a significant amount of neutron radiation in the treatment room. although small compared to the dose the patient receives in the useful beam. So the treatment room and door must be shielded against this neutron radiation, and that may impose special requirements. It can also cause activation of materials in the head of a LINAC so that they become radioactive. The threshold energy above which this reaction begins to become important is 7 to 15 MeV. For LINACs with beam energies higher than 10, that may be significant neutron production. So we've looked at several different mass absorption coefficients. If we take a look at the overall mass absorption coefficient, it's going to be the mass absorption coefficient for the photoelectric effect plus the Compton effect plus the prayer protection. So that's why when they set these there, they said this is for the photoelectric reaction only, this is for Compton only, and this is for pair production. Once you do that and add all of these together, then you've got the total mass absorption coefficient. And it's interesting to note that mu divided by rho is about the same for lead and water at energies of a few MeV. So pound for pound, water and lead are approximately equally effective in attenuating photons with energies of a few MeV. Water does not exhibit absorption edges on this graph because the binding energies of K and L shells are small. So you can see here the contributions to the mass attenuation coefficient for lead as a function of the photon energy. So you can see here, you've got lambda divided by rho, you've got tau divided by rho, you've got kappa divided by rho. So depending on the energy and where the mass attenuation coefficients are, if you were to add all of those together, which is what this represents, this is what you would effectively be seeing in lead. At low energies, the photoelectric effect dominates. At intermediate energies, the Compton effect is what's going to be the most important. At high energies, the mass attenuation coefficient rises with increasing energy as pair production becomes more important. So you have three different regions here. Over here, the photoelectric effect that dominates. Here in this region, which you can kind of see with the energies. Here, photoelectric dominates up to about 7. From 7 to 15, you're seeing this mass attenuation coefficient be greater than the other two. So from about 7 to 15, the Compton effect is what dominates. And then here you can see this effect or coefficient is greater than the other two. So this is why pair production dominates here. So the total mass attenuation coefficient as a function of the photon energy for lead and for water. For low energies, the photoelectric effect dominates and is much larger for lead than it is for water. At intermediate energies, they're going to be roughly the same. And then at high energies, pair production becomes more important than lead. You can try to remember this from the fact that both with photoelectric as well as pair production, they both have a direct relationship to the atomic number. The atomic number of lead is going to be greater than that of water, and that's why these values for the mass attenuation coefficients are greater in the photoelectric and the pair production areas. Here in the Compton area, it's independent of Z, so they're going to be roughly about the same. That's why the graph looks the way it does. All right, so that's going to be the lecture there over 6.1, and the next one will be over 6.2, and we'll see it may go a little further than that.